Okay. So, we are back again. So, this is actually GII, right, and then BII will become, although we will neglect this one, but mathematically we can write. Similarly, BII will be minus sigma of j not is equal to j belongs to I, but j not is equal to I Bij, right. So, under assumptions applied in the fast decoupled method, right, because fast decoupled load flow already you have studied. So, nothing to be mentioned here, right. If you have any doubt at the beginning that already that your power system analysis load flow studies I have covered. So, they are fast decoupled load flow, all assumptions have been made. So, you can go through that or see any book, no problem, right. So, the above AC load flow equations can be simplified to the following equations. Therefore, P I is equal to j belong to I B I j theta I j for I is equal to 1 to n. In this case, what we are doing is that your resistance is neglected, that is why we are writing like this, which can be rewritten as that P I and your theta I j and your theta I j is equal to theta I minus theta j. So, this one you substitute here, you just substitute here, right, then you make two terms. So, P I, that is power injection at bus I, that j belongs to I B I j theta I minus sigma j belongs to I, that B I j theta j for I is equal to 1 to up to n, right. So, equation 04, from equation 04 we know that first term in the right hand of the above equation is 0, right. So, this is your thus we have that P I is equal to minus your j belongs to I B I j theta j for I is equal to your 1 to n, right. So, this is a simple thing. From equation your 4 we know that first term in the right hand of the above equation is 0, because if we come back to equation 4, let me see, right, this is equation 3. 4 is this one, I forgot to mark equation 4, right. So, your this thing this is actually, it should have been equation number 4, I am making it for you, right, 04, right. So, therefore, then we have that your minus sigma j belongs to I actually B I j theta I j for I is equal to your 1 to n, right. So, therefore, this is actually P I is equal to this one. So, the DC load flow model usually has no negative sign, thus B I j is equal to your what you call will be minus 1 upon x I j. Actually, what we will do now, the DC load flow has no negative sign, therefore, we can write like this, say G I j, I mean just in forget about that B I j is equal to actually your 1 upon j x I j, this we know, because this thing. Therefore, B I j can be written as minus j, your later I will make j B I j is equal to minus j upon x I j, that means j cancel both sides. So, B I j will be minus 1 upon x I j. So, this convention will use same as before, although we took minus 1, but DC load flow usually has no negative sign, therefore, we use this one. So, if you do so, then thus you can make it that B I will be just j belongs to I, j not is equal to I 1 upon x I j, this is equation 7. Finally, we establish that DC flow, your what you call DC flow equation will be P I is equal to j belongs to I B I j theta I j for I is equal to 1 to n, right. Therefore, your or in the matrix form we write that P is equal to B theta, this way we can write, where P and theta, first we will see the P, the node injection power, P is the node injection power and its ith element is your given by P I is equal to P G I minus P D. You know that if the P G is the generation at node I and D I is the P D I is the load, then power injection P I will be P G I minus P D I. Here P G I and PDI are the generator output and load at node I respectively, that you know from the load flow studies, and the theta is the phase angle vector and B is the matrix whose elements are defined by equation 6 and 7, right. So, this is actually when you go back to equation 6 and 7. So, B this thing has been defined, right. And another thing is that this equation that this is actually this equation that we have dropped first term is 0, right. So, this equation I told you, above equation I told you previously is 0 4. So, first term in the right hand of the above equation is 0. So, a question to you that why it is 0, right. So, this one finally that your then we can write theta is equal to, from that above equation it is your P is equal to B theta. So, theta is equal to, you are writing that your x p theta, that is x is equal to nothing but your B inverse, right. Sorry. So, this is equation 10 0 1 0 and this is equation 0 1 1. So, if it is so, then similarly substituting the simplifying condition into equation 0 2, one obtain the above power flowing active power flowing into branch P I j, it is nothing but minus B I j theta I j. So, minus B I j is 1 upon x I j. So, its power flow from branch to flow, it is theta I minus theta j upon x I j, right. So, this is actually your what you call that your computation of DC power flow. If you know the voltage angle, if you know theta I and theta j, right, this angle if it is known to you, then you can compute that your what you call that power flow from bus I to bus j, right. So, while making all these equations, again and again I am telling, by chance if you find any typographical any writing error from my side, you just put a question to the forum or you just send an email, right. So, this is actually DC power flow equation. So, next is just hold on. So, just hold on. So, next is that your DC load flow example. Now, for example, let us try to understand this one, right. Suppose we have here actually you will find very simple as far as DC load flow is concerned. Suppose you have a DC load, that is why I told you what is DC load flow little bit, but here whatever we need actually it is very simple thing. Suppose you have a 3 bus problem, right, and this is your slack bus, this is your slack bus. So, this bus is node marked as number 3. So, last bus we have taken as a slack bus instead of marking bus 1, and there are 2 buses, right. Now, this is the flow is given, this is generator. So, suppose is power is injecting here 65 megawatt. So, this 5 megawatt is your 60 megawatt is going to this side and 5 megawatt this direction 60. So, total is 65, right. And here this generator is giving 35 megawatt, right, and this 5 megawatt also, this is 35 megawatt injection and this side another 5 megawatt injection. So, total is 40 megawatt injection. So, this 40 watt leaving this 40 megawatt leaving this bus 3 and going here. So, that means this 60 is coming here and this 40 is coming here. So, total is load is 100 megawatt. So, no loss, nothing is considered. So, it is a perfect balance, right. So, now its reactance is given x 12 is 0.2 per unit, x 13 is given 0.4 per unit and x 23 actually 0.2 per unit, right. So, this is actually will illustrate the principles of state estimation. And then what you do that you suppose now we have connected 3 meters in 3 lines, right, that just hold on, let me move little bit up, just hold on. So, this is actually, suppose we have connected 1 meter here, that your W12 we are telling, right, another meter in line 13. So, W13, another meter in W32. So, it is in line 3 to 2. right, and bus 3 it has cut, actually it is a slack bus, right. So, now the 3 bus system. Now, what is happening? Initially I told you that for all these things, all the data is given, and it is Pg1 your 65 megawatt, Pg3 35 megawatt, PL is equal to Pg1 plus Pg2 100 megawatt. Now, we are measuring this is actually, say this is actually correct one, say. Now, we are measuring the power flows to the line 1 to the line 1 to 3 and in the line 3 to 2 by 3 meters, W12, W13 and W32, right. So, that is your meter placement, right. So, suppose that 3 bus DC load flow was operating with the load and generation as shown in figure 1 I showed you, right. Now, only information we have about this system is provided by 3 megawatt power flow meters located as shown in figure 2. So, this figure I showed you, this is figure 2, right. So, only 2 of these meter readings are required to calculate the bus phase angles and all loads and generator values your generation values fully. So, although only two of these meter readings are required actually to calculate the bus phase angles and all load and generation values fully, right. So, in this case, next we will move to the next page, just hold on. So, just let me increase the size. So, suppose now this wattmeter, when it is reading W12 is 60 megawatt, W13 5 megawatt, W3 is 40 megawatt and base MV is 100. So, W12 0.60, W13 0.05 per unit and W32 is 0.40 per unit. This is perfect one, right. Now, suppose we use W13 and W3, the 2 wattmeter or 2 meter in line 13 and line 32, and further suppose that W13 and W32 gives the perfect readings of the flows on their respective transmission lines. It is a perfect flow, suppose it is giving. Then W13 is equal to 0.05, that is wattmeter placed in the line 13 and other meter placed in line 3 to 2 0.4 per unit, right. Now, then the flows in line 13 and 32 can be set equal to this meter readings. For example, P13 will take 1 upon x13, we have taken that angle instead of theta now, throughout will increase, throughout will assume delta 1 and delta 3. So, P13 is simply 1 upon x13 delta 1 minus delta 3. So, we have given all x13, x32 and x12 values. So, substitute all, so you will get 0.05, W13 is your, that is 0.05, right. So, this is power flows from line 1 to 2. Similarly, and bus 3 is a slack bus, so delta 3 is equal to 0.0. So, delta 3 actually taken 0.0, right. So, with this, if with this x13 is known, so you can calculate what is the value of your, what you call that delta 1, because P13, that is wattmeter reading is here, actually P13 is nothing but W13 reading. Similarly, that P32 is 1 upon x32 delta 3 minus delta 2 is equal to this wattmeter reading, this is nothing but P32 is equal to W32, that is equal to 0.40 per unit, and delta 3 is 0 because it is a slack bus. So, from this, if you know that delta 3 is 0, from here you can calculate what is delta 1, and similarly delta 3 is 0, it is slack bus, from here you can calculate delta 2 because these two are known, right. So, basically this one is equal to 0.05 and this one is equal to 0.4. So, delta 3 is 0, delta 3 is 0. So, from here you can calculate delta value, it will be negative, and from here you calculate delta 1 value, it will be positive, right. So, whatever value you will get, so delta 1, then your delta 1 that is your by 0.4, that is x13 was given 0.4 per unit. So, is equal to 0.05. So, delta 1 is equal to 0.02 radian, right. Similarly, minus delta 2, because delta 3 is 0 here. So, minus delta 2 and x32 is 0.25. So, minus delta 2 by 0.25 is equal to 0.4. So, delta 2 will get minus 0.1 radian as long as that readings are perfect. So, this is the values of delta 1 and delta 2, and delta 3 is 0 because it is a slack bus we have taken, right. So, now we will now investigate the case where all 3 meter readings have slight errors. Now, suppose we assume that meter readings have slight errors, suppose that the readings obtained are, suppose we have taken this reading say meter is giving meter placed in line 1 2, it is giving 62 megawatt. So, 100 MVA base. So, it is 0.062 per unit, right. Similarly, meter placed on line 1 3, actually it is 6 megawatt say. So, it is 0.06 per unit, and meter placed on line 3 2, it is 37 megawatt. So, 0.37 per unit, right. So, in that case what will happen, that Pg1 will be W12 plus W13. You will go back to the figure 1 and simply you add these two reading W12 and W13, better you go to figure 2 where I have marked the meters. So, this is actually 68 megawatt is coming, then Pg2 will be 37 minus 6. So, 31 megawatt, right, and PL will be Pg1 plus Pg2. So, it will become 99 megawatt, and bus 3 is a slack bus. So, here delta 3 is equal to 0.0, right. Now, if you calculate that your P13, that is equal to 1 upon x 3 into delta 1 minus delta 3, that is nothing but W13. So, is equal to 0.06, right. So, because meter placed on line 13 W13 reading is 0.06. So, from here you will get delta 1 by 0.4 is equal to 0.6, because x13 is 0.4. Therefore, delta 1 will be 0.024 radian, right. So, similarly, P32 will be 1 upon x32, that is delta 3 minus delta 2. So, delta 3 is 0, therefore, 1 upon 0.25 into minus delta 2 is equal to 0.37. Therefore, delta 2 is minus 0.0925 radian. With this, with calculating delta 1 and delta 2, if you now you have got this delta 1 and delta 2 values, this delta 1 is 0.024 and delta 2 is minus 0.0925 radian. So, now with this, if you calculate the line flows, that is power your power flows in line 1 to 2. So, P12 will be 1 upon x12 delta 1 minus delta 2. If you do so, x12 is 0.2. So, 1 upon 0.2 it is 0.024 and delta 2 is minus of this one. So, it will be plus 0.0925. If you calculate, it is 58.25 megawatt, right. So, this is the line flows. Therefore, that if you look into this diagram, so this is actually we took these two reading, right, use of W13 and W32. So, these 2 meter readings we have taken, and after taking this one, that we are getting that these 2 readings we can consider, right, that W123 and W322, these 2 readings we consider. Based on that, whatever we calculate the line flows 58.25 megawatt, right. But if you take that this that reading we actually took 62 megawatt, that this your what you call this watt meter placed in line 1 2, it was 62 megawatt, right. But actually we are not getting that, using that 2 data we are not getting that. What we are getting actually, we are getting 58.25 megawatt, right. Similarly, before moving further, similarly if you take these 2 readings, say these 2 reading, and try to find out the, just hold on, let me move little bit up. Now if you take these 2 readings, right, and find out what is delta 1 and delta 2, and based on that you find out the power flows from line 3 to 2, you will find it will not be 37 megawatt, it is something else, right. So, similarly if you take this reading and this reading, this 2 watt meter reading, and find out delta 1 and delta 2, then you will see that this reading is not 6 megawatt, it will be different, That means you have basically you have your what you call redundant readings. You need actually 2 readings, but you have measured the 3 values, right. But in state estimation we will see all these redundant values, that all this measurement we will take, and we will try to go for best estimate later, we will see that. So, in this case you see that it is 58.25 megawatt. Now, this is my 68 megawatt, this is 6 megawatt, right. So, here also it was 68 megawatt, but whatever your what you call earlier we have taken like this one, just hold on, that this one. If you go back to this diagram, whatever data we have taken, actually PL is understandable, but Pg1 was 68 megawatt, because W12 plus W13 is 60 megawatt, right, 68 megawatt. But here if you look into that, here if you look into that, it is not 68 megawatt, it will not be 68 megawatt, it will be actually 58.2 plus 6, right. So, here also it will give you that is your 64.25 megawatt. So, it is not 60 megawatt. Similarly, here it was 99 earlier megawatt, but now 37 plus 58.2. So, it will be load also is not correct, it is giving 95.25 megawatt, right. And similarly, your this your what you call this generation, that your this was this 6 megawatt is you are coming here and 37. So, this total is 37 because 6 megawatt and this is giving you 31, but earlier it was 34, now it is 31. So, ultimately 37 is going here. So, 37 plus 58.25. So, 95.25 megawatt. Similarly, if you consider meter reading of 1, 2 and 1, 3, and you will find this will change. And similarly, if you consider this one and this one, you will find this one has changed, right. That means 3 readings are there. So, which one will be the so you are getting 3 different sets of delta 1 and delta 2. So, but our objective will use all these readings, and find out the best estimate of delta 1 and delta 2, that we will see later, right. So, now you consider W12 and W32. Now, we have considered these 2 readings W12 and W32 only, right. So, in that case your if you look into that W1 this thing, then you will see that your W12 is 62 megawatt and W32 it is now 0.37 megawatt, right. So, this time we have not considered this one. Now, P12 that is 1 upon x12, it will be delta 1 minus delta 2. So, if you calculate delta 1 and delta 2, right. So, you will find delta 2 is minus 0.0925 radian. Similarly, hold on. So, here delta 1 has been computed here. So, P12 is 1 upon x2 into delta 1 minus delta 2. So, that is actually W is equal to W12 reading. So, x12 is 0.2. So, delta 1 put delta 2 value here, delta 1 plus 0.0925 because it is minus. So, delta 1 is 0.0315 radian, right. With this, if you calculate the power flows in the line your what you call 1 3, because we have considered the 2 reading, right. So, if you consider the your what you call the power flow in line, so 1 upon x 3 delta 1 minus delta 3. So, P13 is coming actually 7.875 megawatt, right. Although we have taken this reading that let me go back to the data that it was 6 megawatt, but it is not like that, it is more than 7, right. So, it is 7.875 megawatt. That means that if you plot now, if you see the diagram. So, these 2 readings we took, right, to compute this one. So, instead of your what you call that 6, it is coming 7.875 megawatt, that means this Pg1 62 points plus 62 megawatt plus 7.875. So, it is 69.875 megawatt, right. And in this case the 62 plus 37, so it is got 99 megawatt, and here let me move little bit up. Here if you see this, that your this is 7.875 and this is 37. So, 37 minus 7.875, so generation is actually 29.125 megawatt, right. Similarly, if you take the other 2 readings, you will find a different flow then here line 3 to 2. If you just take this W12 and your W13 reading, right. So, from that note that in figure 3 predicted flows match at W13 and W32, but the flow on line 1 2 does not match the reading of 62 megawatts from meter 1 and 2, right. Similarly, if we are to ignore the reading on W13 and use W12 and W32, we could obtain the flows shown in figure 4. So, that also we have seen, right. What we need is a procedure that actually uses the information available from all the 3 meters to produce the best estimate of the actual angles line flows line flows, bus load and generation. So, what we need is a procedure that will use information available from the all 3 meters. That means, our objective is to consider all the meter readings and try to find out the best estimate of the line flows and the angles, right, voltage angles. So, since only thing we know about the power system comes to us from the measurements, we must use the measurements to what you call estimate system condition, right. Now, recall that in each instant the measurements are used to calculate the bus phase angles at bus 1 and bus 2. Once these phase angles are known, all unmeasured power flows, loads and generation could be determined, right. That means, we need the best estimate for this case, the best estimate of the voltage angle, right. So, we call delta 1 and delta 2 the state variables for the 3 bus system, since knowing them allows all other quantities to be calculated, right. Because our objective is we have to find out the best estimate of the delta 1 and delta 2, because slack bus delta 3 is 0, right. So, in general the state variables for a power system consist of the bus voltage magnitude at all buses and the phase angles at all but one bus, right, that is slack bus. So, note that we could use real and imaginary components of bus voltage if desired, that also possible, Now, if we use the measurement to estimate the states, right, that is the voltage magnitude and phase angles. States means say voltage magnitude and phase angles of the power system, then we can go on to calculate any power flows, generation, loads and so forth that we desire, right. Sorry. The transformer taps and phase angle regulator positions should also be considered as state variables, right, since they must be known in order to calculate the flows to the transformers and regulators, right. So, all these things can be considered, right. So, now next we will go to the what you call that this thing. Now, if we return to the 3 bus problem, if we return to the 3 bus DC power flow model, we have 3 meters providing us with a set of redundant readings with which to estimate the 2 states, that is delta 1 and delta 2. The readings are redundant, right. Since only 2 readings are necessary, you have 3 readings, but 1 reading, every case we found that 1 reading is actually not necessary, but we have to find out some methodology such that we can consider all the readings and we can get the best estimate of delta 1 and delta 2, right. So, the other reading is always extra, because 1 reading is always extra, we have seen. However, the extra readings does carry useful information and ought not to be discarded summarily. So, we cannot just discard this what you call this reading, right. So, we have to find out some technique such that we will consider what you call, I mean in this case what is happening, number of state variables are 2, but number of measurement is 3, because we have 3 readings. So, number of state variables is greater than your number of measurement, right, number of measurement, right. So, similarly it is possible that number of measurement and number of state variables are same. This will be another condition. Another condition may be that number of state variables are more, but number of measurements are less, that we will see later, right. So, thank you very much, we will be back again.